Well, welcome back. This is Math 168. I'm Professor Needing, and this is section 2.7, data visualization and multiple representations. In this one, we'll do very little calculating and more looking and talking about things that are of interest to us. And I'm going to get rid of those things that were in my way right there. So one of the things that we want to look at with inside this section is the importance of a multivariable. And inside of a multivariable, we have different ways of visualizing. For instance, we have these things called augmented scatter plots. We have geographical data, and we have data over time. These are things that weren't available to us back in the day when it was paper pencil and we were looking at stagnant pictures on a two-dimensional graph. Now with the utilization of technology, we have some very nice things that we can do with graphs. They're very creative and they're very inactive in their visualization, and we'll go to some today. But the first thing we're going to do is talk about a little bit of data here. So we have this kidney stone treatment, and in this kidney stone treatment, we had treatment A and treatment B. Treatment A was an open surgery, and treatment B was they call it PCNL. This treatment was a cheaper, less invasive treatment, but the question is it as successful? A treatment is deemed successful if the stones are gone or less than 2 millimeters after 3 months. So let's just look at the raw data. When we look at the raw data of everybody, treatment A had 273 successes and 77 failures. So therefore, it had a 78% success rate. When we look at treatment B, it appears that we have a better success rate, 289 successes. And so 289 divided by the total number of cases gave it 83%. So it beat out A by approximately 5%. So the question is, which is better for removing kidney stones? Well, you would think that treatment B, right? But when we bring a third variable in, it says we also have data on the initial stone size. So we have data about when it's small or when it's large. And the question is, does the most effective treatment depend on stone size? Well, back here, it was just flat out treatment B was better at 83%. Okay, well, now let's bring in a third variable. And I'm going to shrink down just a little bit so we can see all this at the same time. So when we talk all stones, there's that top one that we just got done doing. And I'm going to get my markup tool. So we had 78 and we had 83. End of story. Done. Finished. Voila. Now, what happens when it's a small stone? Well, when it's a small stone, we have 81 successes at a 93% rate for treatment A. So treatment A is clearly the winner when we talk about small stones. Well, that kind of contradicts what we said up earlier about all stones being B. Okay, well, let's look at the large stones because it must be the opposite, correct? Well, when we look at treatment A, that is 73%, and treatment B had a 69%. Wait a minute, how does that happen? So how is it that we have treatment B is better when we look at everybody, but when we break down the treatments into smaller groups, treatment A wins 2 times? Okay, well, let's take a look. First of all, treatment A is used more often on large stones. So if you look at the data and you go back to large stones, 192 versus 55, there was a much higher usage, driving the percentile of success values up. 2, large stones are harder to remove successfully. So when you talk about these, it's harder to actually get a good success rate. That's why more attempts at this can drive the percentile up. If you look at the small stones, you can see that B was used quite often. So in something that was easy to do, a small stone, B was the clear winner because it was used so often, driving its percentile value up here. But treatment A was very good at what it did, even though it was used a very small amount of times. So therefore, over the course of time and lots of repeated usage, a percentile, we won't call it a misalignment, but a percentage can be deemed as being better when in fact something else was better when the third analysis is brought in. And hence the part of this that matters for what this section talks about. If we ignore stone size, treatment B appears to be more successful, just based on the numbers. However, though, when you take a count size in of a stone, we see that treatment A is more successful in both large and small. This is known as Simpson's paradox, in that An observed relationship between two variables can change or even reverse, which it did in this case, when a third variable is brought into consideration. Although a true reversal is rare, often the relationship between the two variables differ when a third variable is taken into account. It says in observational studies, the true story between the two variables can be obscured by a third variable. Okay? So when they talk about breaking it down, put it into categorical data which can be understood. Breaking the data down into this third variable really brought new insight into the data that we looked at. It says new insight can be brought into a relationship with two variables by just simply introducing this new subgroup. Any of the statistics or visualizations we learn from two variables can be broken down by categories or subgroups. So remember, when you go to categorical and quantitative, now you're talking about, for instance, when we looked at side-by-side box plots. Here you can look at the breakdown of kidney stones. And if you look at the left-hand treatment, they're all very, very close to each other. But when you look at the breakdown by small stone and large stone, you can see the very large discrepancy between the two. Very large discrepancy. So this is kind of where we get into augmented scatter plots. So we can add additional variability to a scatter plot in a variety of ways. One, we can make point sizes proportional to the quantitative variable. We can change the color of the categorical variable. We can have symbols which base themselves on the category, and we can animate the scatter plot and change over time. Any interactive feature where the mouse hovers over mouse clicks or touch or any other user input is considered an augmentation of that particular chart. We're going to look at some here. Now, these are 3 short videos that are very good to watch. They're a couple of minutes. It would be ludicrous for me to show you a video while you are watching a video of me. So I would highly recommend that you go take a look at these videos. And they show you some really fascinating pieces about data and how we look at things and visualize them. I'm going to show you some actual charts here in a second. Some of the things that we look at when we talk about data are incorporating the size of the scatter plot, changing things over time, changing geographical data, what we call heat maps. For instance, if I were to look up a simple heat map, and get myself some images, this would be a heat map. And all of you have seen some type of heat map before, where it shows you a Doppler radar is a heat map. Where is the storm the hottest, and where, by hot meaning intensity, and what do you see? It's not always a storm. It can be a lot of things, like geographical regions in a map that's going to show us something. Here's a Doppler one here. Here's a different one here for heat generations. So heat doesn't specifically just refer to heat itself. Especially with the election coming up, a lot of heat maps are being generated for blue and red. These techniques are combined with 1 or 2 varied methods, and they go a long way. And they do. They make a huge difference in a map. To go beyond the statistics graph, the last 2 visualizations are very dynamic, and they show how graphs change over time. The internet enables us a slew of interactivity. And for each of the following, visit the website for a richer data visualization. So let's do that. So first of all, we've got some different looking maps here that are pretty cool looking. And I'm actually going to go to this link, and you can visit that link. And there are many, many different maps here that you can look at. But the maps I'm looking at, like for instance, I'm going to look at this one right here. Wait for it to load. Data, sometimes if there are thousands of data points or hundreds of data points, that it can take quite a while for something to load up. And so you can see this is what we refer to as an interactive visual map. As I float over the icons, different things come up and come out to viewpoint. If I were to actually click on something, I get a value that comes in there. Okay, so I get things. It's very nice. I like that. Take a look at something else right here. Visualization of an election. And this visualization of this election, as I float over time, I can see the changes in that value. I can also see my data points, and I can pick different data. So the map is interactive as I, the user, change it. This is what we talk about when we talk about making something into an interactiveness. How about right here? So if I look at, I lost the map. Where's the map? Oh, here. So some of the maps up here, it shows Twitter. If I go to maybe enforcement rules, as I change in different pieces, it gives me different values. And the maps are interactive again. Very cool. Never would have had this back in when I was in school. You just had to look at a regular map. So this would be kind of like a heat map possibly. And as you change to different NBA selections, it changes what's going on in the map. Okay. The other one was all, and this is just Detroit Pistons. And you can zoom in, you can zoom out too. Okay. And you can even find your area. So if you want to find your area somewhere, you could simply go into that particular geographical area and you could select from there. And you can see that obviously it's hot around that particular area. Political polarizations. These show the left and the right wing, and then the mix shows the Democrats, Republicans. And you can go to these links and you can check these too. But this is just an overlay of color. And when you look at these overlays of color, and here's the polarization right here on the right, again, it gives you a little bit more interactivity into the situation. Oh, it's down here. A little more interactivity, and it shows you just a little bit more than you would have just seen from a normal spread of data. Okay. And there's a little bit closer up on it. These polarizations drive me crazy. The dots, I really have a hard time with, but it's the density of the colors. Here you can see there's a smattering of a little bit of everything. There's a little deeper red in the top right-hand corner, whereas down here that the blue and the red party, or whatever this is for, is clearly split. And these are over years. You can see years in the top left if you blow these up and take a look at them. Family income and college chances. So on the explanatory, we have income percentiles, and on the prediction, we have percent of children who attend college. So you can see we have a positive correlation, an association, doesn't mean a causation. But what we do seem to see is a trend of data as parent income percentiles increase to higher percentiles. Remember, we've talked about these percentiles. Then the chances of a child attending college seem to increase. Well, no kidding, right? I'll see how this interactive map works for me. And we get to draw some things actually in here. So free tip, your line goes through here. So, oh, look at that. That's very interactive. That's pretty cool. And so we can actually make the map itself and we can look at it. So this is the percent of children who attend. I didn't want attending one. I actually wanted to see that one. So somebody made that one right there from some data. So let's talk about Wiley here for a second. And I'm not going to do this question for you, but I'll help you along with it and show you where to go to it. So one of the questions is, it talks about, if you go up top, the set on the vertical axis age is first marriage women, and the horizontal axis babies per woman. Okay. So remember that. Set of vertical axes, age of first marriage. So I'm going to click on here. This graph that opens up is pretty intense. It's got a lot of stuff going on to it, but I'm going to show you that you can change the axes on the left and the right. So this is an interactive bubble map. It's very cool. If you float over any one part, you get that one part, and it changes colors and density. But look at the left and the bottom. So income is not what we wanted. If you remember, what it wanted from you was on the x-axis, age of first marriage. So I clicked on the x-axis, and if I go up here and I start typing in age, and I'm looking for age of first marriage, and you'll be able to come in and you'll be able to find that. And you might even be able to search out easier if you do marriage. Oops, sorry. There it is. See it? It narrows it right down. It was the only one. So age of first marriage becomes my x-axis. What did they want on the y-axis? The horizontal axis. Let me see. Oh, I'm sorry. The vertical axis was supposed to be age of first marriage. Boy, I messed that up, didn't I? So the vertical axis is the marriage one. There you go. Now look, my data is perfectly lined up. Why? Because I got them both on the same axes. So now I have to go back and I got to change the horizontal axes to babies per woman. Okay, so I'm going to go down here. I'm going to type in something in here. I'm going to type in babies per, and there it is, babies per woman. Boom, got it. So this is the data that you need to utilize in order to look at that question. You can also substrain it out by simply clicking on only the area you want. So if you only want Costa Rica, just hover over it and it will show you Costa Rica. If you want Cyprus, hover it and it'll show you Cyprus. It'll show you whatever you want, and you can change those data values as you need to. Remember, you're between 1941 and 43, and because it says in Russia, I think that I would look at Russia. In summary, we often want to go beyond two variables and see if there's a third variable inside of what we do. This is called breaking it down. Additionally, variables can be added to the scatter plot, size, point, size, symbol, things like that. We saw a couple of different things. Data visualizations can incorporate the geographic over time and be very, very interactive. There are many ways to create this visualization data. This ends for us chapter 2. And so what that means for you is that chapter 1 and chapter 2 examination is right around the corner. So I will be producing for you some kind of authentic review. There is already reviews listed inside of the chapter reviews inside of Canvas. So if you were to go to Canvas quickly, and I've got about 1,000 tabs open right here. And I were to pick up my Canvas account real fast, and I were to log into that, and now we're going to my statistics class, and I would go to my modules. Yours looks slightly different than mine, but not a lot. Just simply find the module that says exam reviews. Here's exam chapter review number 1. Chapter review exam number 1 is in PDF format. It's got a plethora of questions that you can, it's going to come down in PDF as soon as it opens. It's got a plethora of questions for you. This is what I take the examination questions from, not word for word, so don't think you're going to see the exact ones, but I'm going to do the same kind of thing. And then if you look all the way at the end of that review, the answers are posted for you right here. A review is no good if you don't have answers. If you have any questions, feel free to email me, but exam number 1 is just right around the corner for you. Have a good day. I think I'm done for the day. I've done enough today, and we're going to see each other again in chapter number 3.